What's going on, people? Intermediate heat flow lab demo. Intermediate demo. Demo. All right. What do we got? So I chose a small home, insulated it with reflective bubble wrap, something like middle of the road ish in terms of insulation material, actually. But I don't know. I just believed in it. I really did. So here's my house. Um, Beautiful, beautiful piece of architecture. Uh, and I thought that a thicker layer of insulation would do a better job of controlling that heat flow, okay, reducing the flow of heat. Because I figure, well, we found in the practices and stuff like that in thermal insulators and conductors, that the thicker the material, the higher the R value, and the higher the R value, the better the insulator. So yeah, I went with it. And two, like, you wear thicker clothing, you stay warmer. Right? Your thicker clothing does a better job of keeping your body heat from leaving your body and going away from you. Keeps it trapped against you. All right. So those are my choices. I clicked on the link, found my data set, okay, the data set to match with the reflective bubble wrap thick layer, pasted it down in the baseline data table, and then I decided I was going to compare mine to polystyrene foam board insulation, also thick. Of course, if you're going to try and determine the effect of insulation material on performance, you have to hold all other variables constant as much as you can. So if I am comparing a polystyrene foam house to my reflective bubble wrap house, and the thicknesses are different, mine is thick and the other house is thin, well, if the polystyrene foam board house does worse, how do I know? Would I be able to tell whether that's because it did worse because it had a thinner layer of its insulation, or did it do worse because of the insulation material? Or would it be a combination of both? Would you be able to determine that with relative certainty? Don't think so. So yeah, you have to, if you're going to determine the effect of insulation material, you have to hold thickness constant. All right. So that if I am doing thick reflective bubble wrap versus thick polystyrene foam board, and the polystyrene foam board performs better, then I know that's because of the insulation material, not the thickness, because the thickness was the same. It was unchanged between the two. There was no difference there. Okay. So I went into the temperature versus time data set stuff and copied and pasted the temperature data for the polystyrene foam board, pasted that into the table. And by the way, yeah, my baseline appeared, your baseline appears once you, or the correct baseline appears once you choose your house size. All right, see, if I were to switch to large, the temperatures actually change. You could see at 10 minutes it's 75. And whenever I change it to small, the temperature at 10 is 78. So anyway, I'm small house, just for the purpose of this demo. All right, so then I first graph the first graph you need to do is your baseline versus your intermediate, so that you can see the effect of adding insulation to your house. All right, because remember, baseline had no insulation. Now we have it. Can we see a difference there in performance? Currently, here's my graph right now. Is it done? Does it still need some work? It does. Yeah. So what all can we do with it here? First of all, do you notice that, like, the lines, again, looks sad and flat. That's because we're so far zoomed out. Um, our y-axis min is now 0 currently. We need to increase that so that we zoom in on the graph. And when you do that, it's like walking up closer to the mountain. From far away, it doesn't look so steep, but whenever you're actually like in front of it or on it, then you could realize like how dramatic it is. So we need to change the y-axis min. We need to increase it. All right. Actually, first of all, I need to add data points like the data point dots. All right. So let's see here. What all needs fixed here? What all can we, what are the things that we can improve on with this graph to make it better? Got a bunch of stuff. Data point dots. Y-axis min. What would be a good value? If your minimum temperature, your starting temperature, minimum temperature is, oops, wrong data sets, 72, well, an appropriate min might be 72 or 70. Some of you don't like the data points being cut off, so we'll make it 70. Max, if you don't like the data points being cut off, you could change the max to 80. Ooh, 7,080. Something like that, right? No? All right, it doesn't look as dramatic. 78. All right. We need minor grid lines. Grid lines and ticks. Vertical axis. Look, if you're currently the major grid lines are counting by twos, 70, 72, 74, 76, 78. And you see some of these data point dots are falling in this space between 72 and 74. Somebody who's looking at the graph has to approximate where along the y-axis those data points might be. That's not good. You want to create as much precision as possible within your graph. So it'd be a lot of help if you added minor grid lines, okay, to your graph. So vertical axis, minor count. If your major is counting by twos, 70, 72, 74, how many lines would you want between, say, like 70 and 72 so that you're now counting by ones? One. All right. So there we go. We have 70, 71, 72, 73, 74, 75, 76, etc. All right. On the x-axis, the majors are counted by 5, 0, 5, 10, 15. So how many minor grid lines would we need along the x so that it's counting by ones? 1, 2, 3, 4, 5, 6. 4. Horizontal axis, minor count, 4. Yoish! See? 1, 2, 0, 1, 2, 3, 4. Right? If I were to have, say, like 3 is the minor count for the x-axis, what is that even counting by? You know, like, look at this dot is kind of awkwardly spaced. That it goes 0, what, 0, 1, 2, 3, 5? No, I guess it would be what, 2.5 would be in the middle. Anyway, this is a mess. You don't want you shouldn't have to like sit and do mental math to figure out like what the axes even are, to figure out where the data points are. Then just make it easy. Make it so that it's counting by ones. 1, 2, 3, 4, 5. There you go. And then your key or legend right now it's labeled as, I wasn't so picky about this in the baseline, but I think now you're at the age in which, you should probably fix a key or legend. So yeah, they're both labeled temperature in degrees Fahrenheit. That doesn't help. One of those lines is the baseline. One of those is the intermediate. It would probably help to know which one is which, right, at a quick glance. So to edit that quickly, you just double click on the key or legend. The blue line is the baseline. The red, double clicky, quadruple click, is the intermediate. Okay. I think that's it. Looks good. Looks sharp. And then, oh my gosh, look at the intermediate versus intermediate plot. They're see, here is where you see like the effect of being so far zoomed out and not adjusting your mins and maxes and whatnot. They practically look like flat lines on top of each other. And there's actually difference here, but when you're so far away, it's distorted, and it looks like there is no difference between the two intermediates. That's misleading, and that's an issue. That's a problem. So you need to be more precise, have a better designed graph so that the details come out and you can see those subtle differences and therefore make better conclusions, make more accurate conclusions. So here, look, see what happens when we adjust those mins and maxes and whatever vertical axis. See, now you can see there is a difference there. There's a, now you could see between what, geez, which one is the blue? I can't even see. Like, look, the key or legend isn't filled out, and I'm trying to remember which one is which then. The blue is mine. It is the bubble wrap. And the red is the foam board. If you're not sure, look at the data. Go back and look at the data. Clearly, the bubble wrap, my house, heats up more during heating, so because it's not as good an insulator. I just know that, but it heats up more. It goes up to 73, whereas the other house doesn't get up that high. So see, mine is 73, the other 72.5. So if you need to, go up and look at the data just to then label your key or legend. All right. Oops, wrong graph. There we go. Yeah, and then I'd carry on again, fixing the X and Y axis minor grid lines. And the rest looks okay. What we also should do is add subtitles to each of these graphs. All right. So that you can tell the difference between them. How to do that: edit chart, customize, chart and axes titles, subtitle. Okay, this one is baseline and intermediate, or your baseline and your intermediate, because now you're referring to yourself in the third person. And this one is your baseline and your intermediate and someone else's intermediate. Okay. All right. Okay, analysis, delta T's. People, do I really need to go over these? I mean, how many times have we done these calculations? All right, heating temperature change. Okay, heating temperature change is the final heating temperature, the temperature at 10 minutes, minus the initial heating temperature, the temperature at 0. Drawing tools. So this is heating, okay, from 0 to 10. So final heating, okay, which is 73, minus initial heating, which is 72. All right. And it would be the same for the baseline. All right. Heating is from 0 to 10. Okay. 78 minus 72. Final heating minus initial heating. Okay. Cooling. Cooling temperature change. Cooling occurs from, let me swipe down here. No, that's good enough. All right. Cooling occurs from 10 to 20. Okay. So it's final cooling, the temperature at the end of cooling, okay, 20 minutes, minus the initial cooling, the temperature at 10 minutes when cooling starts, when heating finishes and cooling starts. All right. That's cooling. And then net is overall. Okay. The very last temperature, which is TCF, final cooling, minus the very first temperature, THI, the initial heating. This is net. Right? Okay. Well, that's some interesting shapes there. What do you see? What do you see in that? All right. Clear this out. Clear it. Clear. I probably shouldn't do that on camera. People might think I have the Roners. All right. So final heating minus initial heating for heating temperature change. What am I calculating for? Is this a baseline? Intermediate. My intermediate. All right. Final heating is 73. Initial heating is 72. Make sure you include your units. Snag. All right. And then the third line, of course, is your answer. 73 degrees Fahrenheit minus 72 degrees Fahrenheit is 1 degree Fahrenheit. I like that. That loosened up the back a little bit. All right. Delta TC, cooling temperature change. Final cooling, TCF minus TCI, initial cooling. And you should get a negative number with this. That negative tells you that it went down. Okay, final cooling is 72.5. Initial cooling is 73. All right, and then the last line there is your answer. 72.5 minus 73 is minus 0.5 degrees Fahrenheit. All right, net is the final cooling, TCF, minus the very initial heating, THI. So the temperature, final cooling is 72.5, initial heating is 72. And then the last line in your calculation is, well, the answer, 72.5 minus 72 is 0.5 degrees Fahrenheit. Okay, now you should have gone into the shared intermediate results sheet and posted your, your name, all your information, your installation material, thickness, and then your delta T's, right? Because other people are going to need them. So that they can compare, determine if their house did better or worse, or their insulation material did better or worse, and so on. All right, conclusions. What climate did I choose? Okay, let's break this down. Kids, it's time to get real. So in a hot climate, let's say, all right, let's say that, my reflective bubble wrap house all right, versus a house with just a single sheet of paper in it, right? In a hot climate, let's say my house is in a hot climate, my the job of my insulation is to keep heat from entering during heating, all right, so that the inside stays cool. This insulation will slow down that transfer of heat as it's trying to go in, as it's trying to go inside. It will slow it down. If it's really good, the heat will take forever to get in, and very little of it will get in by the end of the 10 minutes of heating. Right? If it's terrible, it won't slow it down very much, and the heat will speed right through, and you'll get a lot of heat able to get in that 10 minutes of heating. Okay. Um, Ultimately, really, like the problem, what people get hot climate people get hung up on is that if they use a good insulator during heating, then they're afraid that the heat will get in, but then it won't be able to get back out during cooling because that insulation will now slow down the transfer of heat as it's leaving, and most of it will be stuck inside. My proposal is that why don't you just insulate the house as good as you can so that you stop all heat from getting in the first place, and then you don't have to worry about trying to get that heat out during cooling. You know, if you have if you have a heating temperature change of 0, then you're automatically going to have a cooling temperature change of 0 and a net of 0. It's perfect. Okay, that's the goal here. So in a hot climate, the best insulator is the one that keeps minimizes the heating temperature change, keeps heat from getting in, and then there's no heat inside, and so therefore there's no heat to have to lose, and you have a cooling temperature change of 0 and a net of 0. Right? That's the best how the best insulator would work in a hot climate. Now, if you do have heat that gets in, all right, say if in a hot climate some heat does get in, you get a degree Fahrenheit of temperature change during heating. Right? That insulator, if it's still decent, may keep all that heat inside during cooling, and you might not have any temperature loss during cooling in a hot climate. Okay, that could be a sign of a good insulator as well, as opposed to a house without insulation, okay, or a house with just insulation of only paper. A house with insulation of only paper, it's going to let more heat in, and it's also going to let more heat out during cooling. All right. Isn't that a good thing? Not really. Would you want to be in a house in a hot climate whenever it gets up to like 100 something degrees during the day, and you're like, well, this is all okay, people, just wait until it cools down and then we'll feel cooler? No, you want to keep the house as cool as possible all the time, even during heating. Okay? So, by comparison, even though like the paper is letting more heat out during cooling, that's still not a good thing, really, because it let so much heat in during heating. Right? So the better insulator is the one that lets a little bit in, but maybe keeps more of it in during cooling. But that's not as big a deal because not much heat was let in the first place. Okay. Now, in a cold climate, and let's look at this from the perspective of a cold climate. In a cold climate, the goal is to let in as much heat as possible. Let in as much heat as possible during heating, and then keep it in during cooling. Now, the problem that cold climate people face is that if they choose a really good insulator, then that will block all heat from entering during heating, which is a problem for them. Okay, so they, in a sense, will have the same results as the hot climate house, But for them, that's not entirely good because they weren't able to gain any heat. All right, so as opposed to like if you have in a cold climate, if you have a house made of paper, sure, yeah, you're going to gain more heat during heating, but you're also going to lose it when it's most important during cooling. You're going to lose more of it. So again, for a cold climate, the better insulator is the house is the house that lets in. The better insulator is the house that lets in a little bit of heat during heating, but then keeps that a little amount of heat during cooling. Okay. The key to cold climate success is obviously then, well, not entirely the insulation. They're missing a key piece that's vital to them that will come in the next investigation of the house: windows. Okay. If you think about it, if you have a window, if you have a window, then heat can get in during heating. And then as long as you cover it, then insulate it for cooling, it can't get out. So this is like the sneaky way of letting heat in and still utilizing the positive good effects of your good insulation. Okay, because it will come in through the window, but then stay in because of the insulation. All right. Rad! What did I type? HTG. Okay, so here's how we can see this in the data. So if we compare my bubble wrap home to another home that is using the high density polystyrene foam, what happens here? Let's see here. So my home heats up more, lets in more heat, okay, during heating. Okay, lets in more heat during heating. So the bubble wrap is we have a higher heating temperature change. It lets in more heat during heating. So therefore, it must have a lower, if we're keeping thickness constant, okay, thick to thick or thin to thin, the bubble wrap must then have a lower R value and a higher K value. A lower R value because it's not as good an insulator, and a higher K value because, well, it's not as good an insulator and it's a little bit of a better conductor, all right, than the high density polystyrene foam. During cooling, I also lose more during cooling. And that's consistent with a lower performing insulator. A lower performing insulator will let in more heat, but also let out more heat during cooling. Okay, so, and if we were to compare, say, cotton wool to paper, cotton wool doesn't let in any heat. Okay, so therefore it doesn't have any heat to let out during cooling. It stays flat the whole time. The weight of the sound is in my head. Okay, as opposed to paper, let in more heat during heating, and because it's not as good of an insulator and a little bit of a better conductor, it let out more heat during cooling. Okay? Thickness. Now, if you compare, even just looking at the data alone, if you compare thin to thick for each material, what do we see? So looking at, say, bubble wrap, thin to thick, with a thick layer, it lets in a degree Fahrenheit. With a thin layer, it lets in a degree and a half. Okay, and with a thick layer, it lets out a half a degree, but with a thin layer, it lets out a full degree. So the thicker layer is performing better because it's letting less in and also letting less out. The thinner layer is letting more in, but also letting more out because it's not doing as good a job. And you should find that pretty consistent, thin to thick, among all material types. Okay. Now, again, in this section, if you are comparing the performance of insulation thickness from house to house, if we're focusing in on thickness, then you have to hold all other variables constant. And now that includes material type. So if my house is bubble wrap and I have a thick thickness, all right, then I should be looking for data in which the material is the same, okay, reflective bubble wrap, but the thickness is different. So it would have to be then thin. Okay, the thicker performs better in heating and performs better in cooling. Or no, wait, where am I? This is, okay, I need to fix that. So again, if you are comparing or trying to determine the effect of insulation thickness on the performance of the house or how much heat comes in and gets out, you have to hold all other variables constant. If you were to compare two houses that have both different thicknesses and different material types, and the one house does better than the other, could you definitively conclude whether that was due to the thickness or maybe it was due to the insulation material or a combination of both? You couldn't. So you have to hold all other variables constant. If all other variables are held constant and the only difference between the two houses is the material thickness, then you can conclude that it's because of the thickness that the one house did better. Okay? It's a wrap. Pew, pew, pew.